So now I'm going to give the proof just of the existence that you can factorize. And basically, we're just going to go through this type of argument. This was the first factorization. It was one of the factorization trees for 280. The uniqueness we'll prove in a few videos from now. So the theorem is as follows. Every natural number bigger than 1 is a product of primes. That's the existence of a factorization, and there'll be many. So the proof, well, it's motivated by what we did here. So in general, take any natural number n bigger than 1 and consider the factorization tree for n. What we claim is that if we follow the process before, we bifurcate if we can. So we start off with n. If n is prime, we're finished. If n is not prime, then it's going to be a product, probably in many different ways, of two smaller numbers. That's the important point, that those numbers will be smaller. So that's a bifurcation, and that's what happened here. In the case of 280, we split it into 4 times 70. Now again, the 4 and 70, because they're not prime, then they'll bifurcate into two smaller numbers, and in the case of 70 in a number of different ways. And then once again, well, we don't have any more bifurcation here or here, but the 70 would bifurcate into 7 and 10. The 7 is prime, so the tree doesn't bifurcate there. And the 10, well, that's going to be 2 times 5. And now we've got prime. So in general, what's going to happen is that at each level, we'll have bifurcations as long as we have non-primes. But whenever we have a bifurcation, for example, as here, the numbers lower down in the tree. Oh, I should say something. Why do trees grow downwards? Well, it's just conventional in mathematics and in computer science to have trees growing down. So anyway, back to the important point. The 70 bifurcates into 7 times 10, which are smaller numbers. So as long as there's bifurcation, going down any one of those branches, the numbers will get smaller, strictly smaller. So eventually, every branch must stop bifurcating. Well, since the numbers get smaller, if we started off with n, it would certainly stop bifurcating after n levels, but always, in fact, much sooner than that. So every branch stops bifurcating, and there's only finitely many branches. Well, why is that? Well, once all branches stop bifurcating, we've gone down a certain finite number of levels, at most n, and the number of branches has at most doubled at each level. So we still only have a finite number of branches. So that proves the claim. And hence we've proved the theorem, because since the tree stops eventually, then we just read off at the bottom level all the numbers we have, which are all prime. That's the end of the proof.